We can use our light equations to solve more interesting things as well as just converting between wavelength and frequency and energy. And that's what I have here, right? We have a wavelength of 532 nanometers on a laser pointer. We also know its power, which means we know how much energy it puts out in 1 second. We're going to turn it on for 5 seconds and figure out how many photons we make. And what I want you to be aware of is when you use the energy equation, E equals hc over lambda, or E equals h nu, what you've just calculated is the energy of a single photon. So when I take h times speed of light and I divide it by the wavelength, I get the energy in joules of a single photon. Remember, seconds cancel seconds, meters cancel meters. But there's going to be more than one photon, right? We should definitely get an answer out of this that is larger than 1. We should get a lot of photons. What we know is that we took this powered laser, right? 5 times 10 to the negative 3 is 5 milliwatts, and joules per second is how we break down a watt. And if I multiply that by the 5 seconds that I leave it on, I get a total power of 2.5 times 10 to the negative 2 joules. Okay, if I know the total energy of all the photons, and I know the energy of a single photon, then it's very easy from that point to just get the total number of photons that come out. All right, so we said earlier that light acts like a wave because its crests and troughs are capable of interfering with each other, canceling each other out and leaving dark spaces, or constructively interfering and leaving bright spots. Turns out that electrons can do the same thing under the right conditions. Electrons apparently have waves or crests and troughs that can reinforce each other and make bright spots, or cancel each other out and leave dark spots. And so this experiment was showing that matter has wave properties, right? We thought that light was a wave and it turned out to have particle properties. We thought that electrons were particles. They turn out to have wave properties. And so now we have to deal with that in some way. And the way that we deal with that is using what's called the de Broglie relationship. So de Broglie was a French scientist, and he proposed that the wavelength of matter, right? In this case, we're usually talking about matter, an electron, a baseball, a kid, something like that, right? And we measure that in meters, is equal to Planck's constant, right? That's the same Planck's constant, divided by the speed that it's traveling in meters per second, times the mass in kilograms. Units are really, really important to this, so pay attention to those units. So I just want to show you, let's do a calculation. Let's take an electron, something very, very, very light, traveling very, very, very quickly, the speed of light. And this is an equation that's what we call plug and chug. You put the numbers in, make sure all your units are right, and then you can pull them through. All right, I take Planck's constant, and I divide it by the mass. That's why it's down here. And I divide it by the speed. That's why meters are in the denominator and seconds are in the numerator. And those things, by the way, cancel with things left in the joules. As long as you put your mass in kilograms and your speed in meters per second, the thing that comes out is going to be in meters. And we find out that the wavelength of that electron moving very, very fast and is very, very light is around 10 to the negative 12 meters. So 2.42 times 10 to the negative 12 picometers. That seems really small, except to say that that's around the size of an electron itself. So the electron's wavelength is around the size of its radius. That's important to us because that means that I care about the de Broglie wavelength. Because an electron is tiny and its wavelength is about the same size, that is why I get that diffraction pattern. What about with a thing like a baseball? If I take something much, much larger, 0.145 kilograms, thrown by a pitcher that can't accelerate at the speed of light, right? Something much, much slower. So this is bigger than an electron, but slower than an electron. What do I find out? I find out that it's de Broglie wavelength. And by the way, I had better convert first, right? I need my mass in kilograms. I need my speed in meters per second. I find a de Broglie wavelength that is tiny. That de Broglie wavelength is 1.14 times 10 to the negative 34 meters. If we go back and we think about the electron, that's 10 to the negative 22 times smaller. And if I think about 10 to the negative 34 in comparison to a baseball that has a diameter of a few centimeters, we can tell that I'm not going to be seeing diffraction patterns on baseballs soon enough, or anytime soon. They're simply too heavy and too slow, right? When is wave particle duality important? It's important for very, very small things, like the electron, traveling very, very quickly near the speed of light.